talk about elliptic curves and meromorphic modular forms. And you see these little decorations in the title because due to the interest of time, I guess I'm only going to focus on weight 4 and level 1 basically. But everything can be generalized to higher weights. So maybe let me first start by discussing two prototypical examples of meromorphic modular forms that I want to discuss. So let's look at E4 over J and E4 over J minus 1728. So we can still write down their Fourier series expansion formally, and if you do that, you'll realize that actually they both satisfy that n divides the nth Fourier coefficient for all n. And this is the part where, like, when I practice my talk, I would mention that here Li stands for Yingkun Li, who is in the audience, but unfortunately he's already left. Okay, but actually, moreover, we can prove something more. We can even sort of, you could say, like, describe the p-adic property of these two meromorphic modular forms. So you don't really have to, I guess you don't really have to know what exactly these two congruences are, but basically what I want to highlight here is that if you choose L to be 1, then you can see that modulo PQ, these two meromorphic modular forms are like UP eigenforms with eigenvalue basically plus or minus P depending on P. So here we have two modular forms that are of the form, I guess one is E4 over J minus 0, and the other one is E4 over J minus 1728. So I guess the natural question to ask is like, what if we consider E4 over J minus any integer or any rational number, let's say? And since I have an elliptic curve in my title, I may as well take an elliptic curve and consider this E4 over J minus the J invariant of the fixed elliptic curve that I take. And you see that I actually don't want the J invariant of this elliptic curve to be 0, 1728, because those are very special. I mean, those are two special cases that sort of does not really fit into the general discussion. But if we look at this meromorphic modular form, we also observe something interesting. So if we take a group prime of the elliptic curve, then it seems that the p coefficient of this meromorphic modular form is congruent modulo p to the square of the AP of the elliptic curve. And if moreover the p is a supersingular prime, then the p coefficient is in particular divisible by p squared. I mean, if we just look at the first congruence, in the supersingular case, the p coefficient is only a priori divisible by p, but actually it is divisible by p squared. And maybe I also want to remark that if we are considering weight k, then in the supersingular case, the p coefficient will be divisible by p to the k minus 2, basically. So it will be really high p-adic valuation. And I also want to say that, well, previously we sort of obtained, in some sense, the exact p-adic behavior of those two meromorphic modular forms. And here we could also do that if we are willing to separate the cases of ordinary primes and supersingular primes, basically. And you can also see that in the supersingular primes, you sort of obtain very high congruences, like high prime powers, basically. On the other hand, there is also a different perspective that sort of can unify this ordinary and supersingular dichotomy, but via a slightly weaker congruence. And this slightly weaker congruence actually also relates this meromorphic modular form to the symmetric square of the elliptic curve. So in some sense, I was hoping, well, I hope to convince you by the end of my talk that this meromorphic modular form, even though it is a GL2 object, it looks like a GL3 object. So let us recall the characteristic polynomial of the Frobenius at P of the symmetric square of the elliptic curve, which would be x minus alpha p squared times x minus alpha p beta b times x minus beta b squared, where alpha p beta b are just the two roots of this projective polynomial. And what we observe for this meromorphic modular form is the following. So P is still a group prime of E, and then we see that basically we just replace every x power term by some coefficients of this meromorphic modular form. And this particular linear combination is, well, 0 modular high power of P, basically. And also this congruence is also satisfied by if you consider E4 over J minus JE raised to some power, then the exact exponent of the P power will sort of depend on R. And another perspective that I sort of want to highlight here is that if we let ft of x to denote the characteristic polynomial, then you could plug in UP to FP and then apply it to the meromorphic modular form. Then you see that it is 0 modulo higher power. So I guess what I was trying to say is that this meromorphic modular form, like modulo higher p power, it sort of looks like it satisfies the Frobenius relation, or like the Hacker relation satisfied by this symmetric square of the elliptic curve. So I don't know how to prove this, but I hope to still convince you that this should be true. So are there any theoretical reasons, or I guess heuristic reason of why this is happening? Okay, let us fix some point on the alpha plane and suppose that maybe J Marion is a rational number, and let E of alpha to denote the elliptic curve corresponding to the alpha. So let us consider this particular span. So it will be a three-dimensional space, and I sort of want to convince you that this is the three-dimensional space that corresponds to the three-dimensional symmetric square of the elliptic curve. And you see that this three-dimensional space is sort of, I guess, non-canonically isomorphic to this the space of meromorphic modular form of wave 4 having a pole at alpha, proportionally by the derivative of the space of meromorphic modular form of wave -2.
Isomorphic as what?
Sorry?
Isomorphic as what? In which category?
Oh, I just meant that they are sort of non-canonically isomorphic as the vector space, basically.
This means just dimension 3?
Yeah.
Suppose that the points on the left are not in the image of D3.
Yeah. So basically, I just want to consider those that are not in the image of the bubble. And I think this is correct. So basically, I want to say that in a recent preprint by Francis Brown and Tiago Fonseca, they sort of established a relation between meromorphic modular forms, cohomology and of puncture modular curves, and symmetric powers of the elliptic curves. And in my case, their relation sort of specializes to this following thing. So here, the left-hand side is this linear span that we are considering. And they relate this to the first cohomology of this puncture modular curve. But then they also relate that to the symmetric square of this elliptic curve associated to alpha. So on the elliptic curve side, we have the Frobenius action. And as we have seen previously, this Frobenius action seems to relate it to the UP action on the modular form side. But I guess there is this one evident issue. So there's no UP operator on the leftmost space, because the UP operator increases to level and they also shift the pole. So in some sense, I don't really know how to solve this issue. But maybe let us pretend for now that there is a UP operator on this modular form side, because this analogy actually works really good. And suppose we specialize to, say, CM case. So now let's pick a CM point on the alpha plane, and here the E alpha would then be a CM elliptic curve. And let us pick a prime that splits in this CM field. So in particular, this prime should be ordinary. And we still have this picture between these two three-dimensional things. And on the elliptic curve side, because we are in the CM case, we know that over the CM field, it sort of should split into three one-dimensional pieces. And on each piece, the Frobenius at P should act as scalar, like alpha p squared, alpha p beta b, and beta b squared. And alpha p and beta b are still the two roots as before. So this means that maybe on the modular form side, we should also expect some splitting, where the UP should act as these three eigenvalues respectively. And I'm going to show you one numerical example which visualizes this splitting. So I will take alpha to be the CM point of discriminant -7, and so the J of alpha is -3375. And consider this particular three linear combination of I guess E4 J plus 375 to some power. And we can observe that, well, basically, the first one looks like a UP eigenform with eigenvalue alpha p squared. The second one is like UP eigenform with alpha p beta b, and the third one with eigenvalue beta b squared. And maybe I also want to highlight here is that, in fact, the second one also satisfies the original divisibility relation that I presented, that it is also true that n divides the nth Fourier coefficient for all n. And I think I will end my talk here.